Okay, I think I'm going to push stuff back so that we have time to talk about 4.6 with questions and actually do a little bit of a lecture on 4.7. So 4.6 will be due Monday, 4.7 will be due Wednesday. But to start, I guess, what questions do you guys have on 4.6 stuff? Okay. The constraint bit. Okay. So lightest. Smallest something. What are we looking for? What's the smallest amount of material? And so how am I going to measure the amount of material in a can? Surface area. Surface area is going to be the amount of material you use to make the can. Okay. So lightest would be the smallest surface area. Okay. And this is going to be our objective function. Right. So the surface area of a can is going to be in terms of the radius and the height. It's going to be 2 pi r plus 2 pi r squared plus 2 pi r h. This is going to be the top and the bottom, and this is going to be the lateral side. 1. Yeah. And see. Open top, yep. So just pi r squared plus 2 pi r h for the lateral side. Okay. And we want it to be able to hold a volume of 8 cubic centimeters. This is going to be our constraint. Okay. We're constrained to only cans that have that. So that's pi r squared. H equals 8. That's our constraint function. Okay. And this is our objective function. And we want exact answers, so we're just going to carry pi around everywhere. And is there anything else to this? I think that's probably it. Yep. Okay. So now what do I do next? Yeah, solve for one of the variables. H looks like it's probably the smallest, the easiest thing to solve for. I don't have to take a square root or carry that around anywhere. So we're going to go H equals 8 over pi r squared. And then we're going to get surface area in terms of just the radius is equal to pi r squared plus 2 pi r times h, which is 8 over pi r squared. So the pi's cancel. One of the r's cancels. Pi r squared plus 16 over r. We want to maximize this. Okay. And so take S prime, 2 pi r plus negative 16 over r squared. Is that equal to 0? So I will move this over to that side. Divide by 2 pi, and then r is the cube root of 8 over pi. H then, which was equal to, was it 8 over pi r squared? 8 over pi r squared. This all simplifies a little bit. I've got 8 on top. I've got a pi to the 2/3 up there. I've got a pi down here. I've got an 8 to the 2/3 down here. So really that's also the cube root of 8 over pi. This 8 is there, right? This? That was what we solved for here. So I'm going to have both the height and the radius are the cube root of 8 over pi. That did it? Okay. Where do we have questions on that? And lightest? Yeah. Other questions you guys have on this stuff? At 15? Okay, we got to draw a picture because I can't figure out what's going on without a picture. Small island, 2 miles from the nearest point P on a shore, which is straight. So here's the shore. It's straight. We've got a island over here. This is 2 miles. A woman on the island is in a boat. And she can row 3 miles an hour and walk 4 miles an hour. And we want to go down shore 15 miles to town. And so she's going to row to shore and then walk. Does this make sense? She's faster walking, so she should at least get some of the way down by rowing, but then faster walking. So this is 3 miles per hour. This is 4 miles per hour. We want to know what x is. Let's call this 0. Let's call this 15. Okay. And so the time function dependent on x is going to be let's label a few more things. Let's label this rowing, and let's label this walking. So rowing, that's going to be the square root of 2 squared plus x squared. That's how far she has to row. Walking is going to be 15 minus x. So far, so good? Okay. So the time, if she has to row this far and she goes 3 miles per hour, it's going to be this divided by 3 miles per hour to get the hours. So square root of 4 plus x squared over 3 plus 15 minus x over 4 is how long she's going to spend walking. All good? Okay. And this was the point that you got where you... Okay. So that's the optimization, and it's already in just one variable, so we don't actually have sort of the constraint was that the entire shoreline is 15 and she's 2 miles from shore and all that stuff together is kind of the constraints. Okay, so t prime, it's going to be 1/6, 1 over square root of 4 plus x squared, and then times 2x minus 1/4. Good with that? Okay. Can simplify things a little bit. That's going to turn this into a 3. So if we set this equal to 0, I get that 2x over 3 square roots 4 plus x squared equals 1/4. We'll cross multiply. 8x equals 3 square root 4 plus x squared. Still trying to solve for this. So I'm going to square both sides. 64x squared equals 9 times 4 plus x squared. So 55x squared equals 36. This is 36 plus 9x squared. So take away 9x squared from both sides, you get this. X squared equals 36 over 55. X equals, well, it doesn't make any sense for her to row farther away from town, so we're just going to go with the positive one. 6 over the square root of 55. And that's not right. Oh, I did cancel it. I canceled it. Yeah, you're right. Okay. So this gives me just 4. Which this makes this 16. Subtract that off, you get 7. So not the square root of 55, but the square root of 7. I didn't screw it up again, did I? There we go. Other questions on that one? So the biggest issue with all of these is always the translating the story problem into math. That's usually the hardest part. And that just takes lots of practice. There's a few general things like draw the picture, label everything that's variable with variables, and then kind of fit the variables together how they're related. But it just takes time and practice. They're patience problems rather than like severe thought problems. Other questions from this section?
Number 8.
Okay, I'm going to do 8 and then 17. So we get a silo without a base. It's going to be a cylinder with a hemisphere on top. So that's going to have radius, right? It's going to be the same radius down there as it is up there. And then the height here is not yet given, but we want the construction cost to be a minimum, which means we have to figure out the cost, and it tells us the cost of the surface area is 8 times as great for the hemisphere as it is for the sidewall. Okay, so the sidewall is 2 pi r h, and then the cost of that is going to be 8 times as big, no, sorry, an eighth as big. So let's just pretend that the cost of the sidewall is 1. Because it doesn't actually give us the costs, right? So let's just say the sidewall costs 1. Per square unit. And then the hemisphere will cost 8 per square unit, since it's 8 times as much. And the hemisphere, the surface area of a sphere is 4 pi r squared. So that's only half of that, so it's going to be divided by 2. And this will cost 8 per square unit. So our total cost function is in terms of r and h, and it is equal to 2 pi r h plus
Those cancel. That's a 216 pi r squared. Okay. Questions on just that, finding that formula? Okay. So this says to do this in terms of the radius, the height, and the volume, right? So we're going to have that the volume is equal to, well, it's going to be half the sphere. So 4/3 pi r cubed over 2 plus the cylindrical part. So that's pi r squared h. That's the volume of the cylinder, volume of the sphere on top. That together will give us the volume. So that's our constraint function. And the one that looks like it's probably easiest to solve for in this constraint is still h. So we're going to think of the volume as a constant, the radius is a variable, the h is a variable. But let's simplify this a little bit. That's going to be a 2. So volume minus 2/3 pi r cubed divided by pi r squared. That's going to equal h. If I solve for this constraint for h, I end up with that, which we can simplify a little bit. This will be volume over pi r squared minus 2r over 3. Because the r squareds on this cancel, and the 2/3 stays, but the pi cancels. That's equal to h. Okay, and so we want to minimize our cost function. So let's find our cost function, plug h in here. So the cost function in terms of r, it's going to be 2 pi r times h plus 16 pi r squared. I'm going to foil, or not foil, distribute this thing in there so that I can simplify a little bit more. 2v over r, because the pi's cancel and one of the r's cancels, minus 4 pi r squared over 3 plus 16 pi r squared. So I'm going to put these guys together. 2v over r minus 16 minus 4/3. It's going to be 13 1/3, which is 40/3. Pi r squared. Is that right? No, that's not right. 13 2/3, so 44/3. 42/3. 16 times 3 is 48, minus 4 is 44/3. 14 and 2/3. 14 and 2/3 is the answer. Okay. Now let's take a derivative here. This is C of R, not with the derivative. C prime of R. That's going to be minus 2v over R squared minus 88 thirds pi R. We want to solve that when we set it equal to 0. So since they're both negative, that's really not any good. This is positive, isn't it? Good. That's bigger. 16 is bigger than 4/3, so we're positive. That's much better. I can actually make this work this way. So we'll subtract over, or sorry, add over. And then I can cross multiply. Get 6v equals 88 pi r cubed. Divide by 88 pi and then take a cube root. So 3 over 44 pi under a cube root is equal to r. V. Should have a V in there. Okay, and then H. We have H in terms of R already. What was H? H was V minus, V over, let's do the simpler form. This guy. V over pi r squared minus 2r over 3. So H is equal to V over pi 3v over 44 pi to the third minus 2 3v over 44 pi to the third over 3. We can do some arithmetic, algebra. I've got a v, I've got a pi, I've got this was squared, right? So that's a 2. I've got 44 pi to the 2/3 up here. I've got 3v to the 2/3 down here. And then here I've got 2 3v to the 2/3. Nope, just the 1/3. And then down here I've got a 3. I've got 44 pi to the 1/3. Okay. So I've got v to the 1/3. I've got 44 to the 2/3. I've got pi to the 1/3. And I got 3 to the 2/3. And here I have a that's 2 times 2 times 11, right? So I've got 2/3 of a 2 down in the bottom. I've got a full 2 up top. That's a 2 to the 1/3 up top. I've got a 3 to the 1/3 up top and a full 3 to the bottom, so I've got a 3 to the 2/3 down there. I've got a V to the 1/3. I've got a pi to the 1/3, and I've got an 11 to the 1/3. That's taking care of everything there. So I've got V over pi to the 1/3 on both of these. I've got 2 to the 4/3, 11 to the 1/3, 3 to the 2/3, minus 2 to the 1/3, 3 to the 2/3, 11 to the 1/3. There's got to be a way to simplify this a little bit more so it's not quite so ugly. I'm going to rationalize denominators by multiplying by a cube root of 3 and a 2/3 root of 11. So I get a 33 down in the bottom. I want my denominator to be 33. I think that'll work out okay. So 2 to the 4/3. I need an extra factor of 3 to the 1/3 up here. I need an entire factor of 11, so that gives me 11 to the 4/3. And that's over 33. And then here, I have a 2 to the 1/3. I have a 3 to the 1/3 because I need an extra factor of 1/3 of a 3. And I have an 11 to the 2/3 there. One more thing that I want to do to simplify. I'm going to factor out a 2 to the 1/3 because that both parts of the numerator have that in common. 3 to the 1/3 because both parts of the numerator have that in common. And I have an 11 to the 2/3 that I can factor out. And then what am I left with? I'm left with a 2. Times 11 to the 2/3. And this just becomes a -1 over 33. And I can write that first bit as 2 times 3 is 6, times 121 is 726. 726 to the 1/3. 2 times 11 to the 2/3 minus 1 over 33. And that's as simple as I think I'm going to make that. Okay, let's plug these in. Hopefully I didn't screw up algebra too badly. The radius, that's the simple one. That's the cube root of 3v divided by 44 pi h. I guess I can do this with roots. Third root of v over pi let's do a fraction. Let's see what I'm doing. So in the numerator, I want 726. I want the cube root of 726. And multiply that by 2, not square root, cube root. 11 to the 2/3, so I want 121. Minus 1. That parenthesis closes that closes that, over 33. Risky check, and we're not good. Can anybody see anywhere I screwed up my arithmetic? Let's just not do any of the as the, yeah, probably. Yeah. V over pi. I want a cube root of 3v over 44 pi. Do the second. Minus 2 3v over 44 pi. Try that. It's probably okay. Yeah. So I screwed my arithmetic up somewhere, but we're good. Questions about that? I didn't even put in the right capital V on the second part there, so it must not be all that picky. But other questions you guys want to look at? Oh yeah, I said I would do 8 and then 15. 17. Sorry, we did 15 already. What 17? Okay. We've got a cart on a spring. It's going back and forth. Let's call this its rest position. So we're going to call 0 its rest position. So it goes out 14 this way. And then it starts bouncing back and forth. We're frictionless, so we get perfect sine function, cosine function. The position is S of t equals 14 cosine of pi t. So at 0, we're here at 14. At 1, cosine of pi is -1, so we'd be at -14. So it goes all the way across in 1, and then it's going to go all the way back across in another 1, and so on. 1 second. So it's moving pretty quick. All right. Maximum speed. Well, just thinking about it, it's going to accelerate until the spring hits the rest position, and then the spring is going to be compressing and sort of decelerating it. So it should be going the fastest at 0. Right? So we can show that by showing that s prime of t is equal to 14 pi sine of pi t with a negative on it, probably. Yeah. Because the derivative of the cosine is negative, and this is equal to 0. When sine of pi t equals 0. So when t is equal to any integer, what is that maximum speed? That maximum speed is, well, if I put an integer in to the cosine function, I will get 1. Like the cosine is 1 when the sine is 0, so it'll be 14. That's not right? Oh, 14 pi. Hang on, sorry. I want the maximum speed, not the maximum. So the maximum position's here. The maximum speed is when the derivative is maximized. To maximize the derivative, we have to take a second derivative. S double prime of t equals minus 14 pi squared cosine pi t. Okay, and that's going to be 0 when we're back to our original starting position, which is where it should be the maximum speed. So to get the maximum speed, we plug one of those integers into the speed function. But these aren't the integers anymore. These are the half integers where we're back here. So this s double prime of t equals 0 maximizes s prime of t, and s double prime of t equals 0 when cosine of pi t equals 0 when t equals pi over 2 times 2k plus 1 for k, an integer. Right. So I want the odd, I want 1/2, 3/2 pi, 5/2 pi, and so on. That's when we're going to get back to the center, because it takes us 2 for a full loop, but 1 to get back to the center, and then 1 to get back to the center again, and so on. Okay. Now we plug this into s prime of t to find max speed. And so s prime of t equals 14 pi sine of, with a negative, pi t. And at these odd halves, this is going to be a plus or minus 1. But since we want the speed, we want the maximum of the absolute value of this stuff. So that's going to be 14 pi. Nearest tenth. Calculator. Nearest tenth is just going to be 44. Okay. At which times is the maximum speed happening? These are the pi over 2's. It wants k's to separate answers. And rounding to the nearest tenth. Oh, for 5 seconds. So we want to go up to 5 seconds. Okay. So 3.14. That's so we'll do those two. Did I round wrong? Sorry? Oh, yeah, it was the second. Yeah, sorry. Yeah, because we decided it was, what do? I don't want these t's in here. Or I don't want this in here because I've already got the pi there, right? So I just get rid of that. I just want the over 2 pit. So yeah. Half, 1.5, 2.5, 3.5, 4.5. There we go. Maximum speed is always at 0 centimeters because that's where its resting spot is. So we talked about that already. The magnitude of the acceleration is going to be 0, right? Because it's changing from a positive acceleration to a negative acceleration. Yeah. And the position of the cart when the magnitude of its acceleration is maximum, that should be at the very ends. Yeah, so at 14. And minus 14. Okay. And we are out of time, so. I will let you guys go. Oh, there is one more part, I guess. So that would be at half of a second. We plug half a second in to the speed function. So that's going to be that 14 pi, right? That's going to be the 44 again. Oh, it wants, what does it want? The speed of the cart when the, oh yeah, the speed of the cart. Yeah, thanks. Okay. All right, I will see you guys next week. I will extend the homework and that sort of thing. Sorry I ran over.